you'd have to make it bigger. So bending on section AA, the projection of the base is 1850, isn't it?
Yep.
Again, 181 kilometres per square metre, so M 181 times 1.85 squared over 2. It's just a cantilever. So that's taking a metre width. We've worked out an area of reinforcement, 1963.
I think it's 309. The solution for that is 309.
Oh, that's what, yeah, whatever it's for, I've got 309 here. 310. I've got it down. So, the force in the reinforcement per metre I've got an effective depth of 0.65. Z is going to lie between, it's got to be more than 0.82 because that's the lower limit for single reinforced section. It's got to be less than 0.95 because that's the upper limit. So, and pad foundations generally tend to be fairly lightly reinforced because the depth is determined by the shear strength to make them deep enough for that. So if we try Z is 0.9 times 0.65. Then the moments, 854 times 0.59. That's the moment of resistance.
$499.6.
How much?
$499.6. Not fine. 499.6.
500.
So there's a fair bit of reserve capacity. Oh, you weren't asked for the bending strength, but you know it's okay from the bending strength point of view as well.
Can you just say again how you chose 0.9 for Z?
Z's got to be between 0.82 and 0.95. 0.82 is the lower limit for an under-reinforced section. Any less than that, we can't go because the reinforcement may not yield.
That'd be the case for single reinforced only, would it?
Yeah.
Because for double reinforced,
yeah.
Yeah.
Your alternative is to use, I mean, you can use the formula in the data sheet in this particular example if you want to. You can use the formula for K to check that it's okay as, you know, to check the ultimate moment, the maximum moment that a single reinforced section can take. And then you can use the formula for Z. You get an exact value for Z, and you'll get a more precise answer. But you know, given that the answer that we've got here is, 160% times the value we need. That's close enough. In summary, we've got Z between these two limits. That lower limit is the limiting value of Z for a singly reinforced section. It's related to X is less than 0.45D, I think. And it's also sort of related to that data sheet formula, which is limiting moment mu is 0.167 BD squared F3K, which I sort of rather warn people against using without thinking about it, because that formula is fine for rectangular section, but it doesn't really work for non-rectangular sections.
What would the sort of limit be for doubly reinforced?
Sorry?
If there is a similar limit for doubly reinforced?
If it's doubly reinforced, that is Z. Right, so if it's doubly reinforced, what you do is you put in the maximum moment that you can put in for a single reinforced section. So you fix it at that limit, put in the maximum reinforcement that you can, and then any extra moment is taken up by putting extra reinforcement top and bottom. So what you do in doubly reinforced section, you say, right, we've taken it to the limit with single reinforced, we've used all the concrete fully, and any extra moment can only be taken by providing some more steel. Yeah?
Silly question. What is Z again?
Z? It's the lever arm. It's the distance between the resultant force in the concrete and the force in the steel. I'll draw it out section. Reinforced concrete section like that. So imagine that's got a beam like this, supporting loads, reinforcing bars in the bottom. We cut it in the middle. We cut that beam in the middle. Then there's an external bending moment, like that, at this point. And that's got to be resisted by an internal moment. Force in the concrete, force in the steel. There's no externally applied force, it's not pre-stressed concrete. The distance between the resultant line of action of those forces is Z, and that's the lever arm. So in this case, we've got a strain diagram like that, and a stress diagram like that. Z is the distance between the line of action of that concrete force and the line of action of the steel force. And that's fine for a rectangular section. If you've got a non-rectangular section, then if you use it in the rectangular stress block, then let's say you've got a circular section bending. The line of action of the force is going to be a bit closer to the neutral axis for a circular section than it is for a rectangular section. If you've got a T section and some of the web is stressed, then the line of action of the force is going to be closer to the top flange than to the neutral axis. So the formula in the data sheet, they only apply really for rectangular sections.
You know, like I said before, when you have a T section, you can assume that the height of the stress block is the height of the flange.
Yeah, T section.
Yeah.
Just go through the whole class.
So you've got a beam like that, and the top flange is in compression, and the reinforcement in tension is in the bottom. A number of possible scenarios in terms of the way it's going to work. First of all, it depends on where the neutral axis lies. If the neutral axis lies within the flange, then obviously the width of the concrete in compression is going to lie wholly within the flange. So your reinforced concrete calculation would be based on that flange width. Now, in terms of whereabouts that the resultant force acts, if that's uniformly stressed, constant depth, constant width rather, the line of action of the force is there, isn't it? In the concrete, it's in the middle of that stressed area. It's in the middle of the stress block. So the lever arm in this case, the distance between the concrete force and the steel force is that. Now, what I suggested when I was looking at the example this morning is that it's slightly conservative to assume that the lever arm, that the force in the concrete acts in the middle of the flange. Right? So what I suggested was, if you do this, as far as the lever arm is concerned, you're making a conservative assumption. Assume that the whole flange is stressed, the line of action is in the middle, and then the lever arm, if that's HF for height of flange, and the lever arm is D minus HF over 2. So that's generally going to be conservative. You can then work out what's the total force available in the flange. You could then balance that with some force in the steel to determine a moment. If that moment's more than you need for the applied moments, and you're not using the whole of the flange, you're back to this scenario, and the assumption that you made about Z is conservative. Yeah, so you're making conservative assumptions, slightly conservative assumptions, just to save you tedious calculation. The third scenario is, I'll draw a slightly different proportion beam here.
No, that's not going to happen. I'm not going to do this question.
Okay, so it's got a thin top flange and a big beam section. There the neutral axis might be down here. Okay, so the stressed area could be that. If you've used this approach for this one, then it's still conservative, because all you've done is you've ignored that bit of concrete there. And that bit of concrete there is sort of closer to the neutral axis than this bit, so it doesn't contribute so much to moment of resistance. So again, the assumption about the force acting at the centre of the flange is a conservative one. If you use spreadsheets for designing reinforced concrete beams, then they'll generate an exact answer for you. But we're not in that business. We're looking at sort of the basic principles, some rudimentary calculations to be able to check the sort of computer output that we're going to get. So this is where the neutral axis lies well into the web, and so there's some contribution from the web as well. Can't go too far with this one though, because if that neutral axis comes further down, then we're going to get into the situation where